Hello friends, and welcome to a chat from the engineering desk. I hope you are all doing very well today. We have got another motor here today. It is, let me move this out the way. It is a Brushless permanent magnet rotor motor, which is currently not got an encoder fitted to it. But inside there's Hall effect commutation signals. Those are these wires coming out here. Your supply and your three signals UVW. And they are wired up to some LEDs. So what we are going to do is power it up, and I shall show you the operation of the LEDs as you spin the motor rotor. Let's get this plugged in and powered up. So there you have it. So as you spin this, you will notice that they overlap. That's the commutation signals that overlap, like so. Okay, and when I reverse the direction, the reverse happens. You see them do that. These wires are currently touching one another, making this a little bit hard to turn. That's better. Because it's a permanent magnet rotor motor, you actually generate voltage when you spin it. Let me show you. Bring in multinational meter. Hook it up to the wires like that. And you can see some voltage being produced. Like so. Because it's a permanent magnet motor. Behaves the same as a DC motor when you spin it. So when you touch those, if you short out a winding by doing this, this becomes hard to turn because you've got current flowing in the windings now. So you've got three wires here because that's obviously a three-phase motor. So that's that. So why don't we take it apart and I'll show you what's going on the side. But why don't we hook it up to a scope and look at the signals, because no demonstration would be complete without hooking it up to a scope and looking at the signals. So we want one channel, two channel, let's move that aside. Now what you need to do is find 0 volts and one of the signals. And find another 0 volts. And another one of the signals. Let's see. Spin the probe around. so. Good. You are connected. So let's zoom you in on the scope. Power it up. Let's just set my probes correctly. Set them both to ×10. And now what we need to do is change that fiddle, fiddle, fiddle. Change that to DC. Channel B. Change it to DC as well. So now let's change that to 200 millivolts. Let's just change it to 100 millivolts per division. Now let's change that time base a little bit. So that's half a second per division. So what we should see is a trigger happening. And let's speed it up a little bit. Trigger. Let's set that back to auto. So if I turn this clockwise, we should see some events. No. Let's see. Change the time base a little bit. So now I'm spinning it counterclockwise. So we should see the shift. The yellow is leading the blue when I spin this counterclockwise. Blue, and I spin it clockwise, leads. Okay. So the two change. If I had a 4-channel scope, we could see all 3 signals. But for now, we can make do with seeing 2 signals. Nothing wrong with that. So now we are done with this. And power that down and put that away or aside. So might just bring it in later. But for now, bring the motor back to view, like so. And let's take it apart, and magically the motor's apart, just like that. So what you have over here is the ring with the magnets in it that provides signals, the magnetic signals for your commutation sensors over here. So that spins inside there. The bearing fits down there with this ring right behind it. There's your commutation signals. So let's see, how's this held together? By screws. Very good. So what we do is we take the screws out, quickly like so, and and this should come out. I think we need a different tool for the job, like so. Oh yeah, there we go. Now let's bring this item closer so the LEDs are visible. And then that, hang on, why don't we vandalize this motor? There's your 4 rows of magnets, so it's a 4-stack motor, and that's how that fits into there. So let's power that up again. As you can see, no LEDs are lit over here. So what we do is we insert that like so, and then as the rotor spins past those commutation, the Hall effect sensors, there you get your signal like that. What we can also do is bring in a magnet. So what do we learn from that? We are dealing with bistable Hall effect sensors. So what you have got is, in the one direction they will turn on. If I apply the magnetic field from the other direction, they will turn on like so. If I reverse the magnet, bing, they will turn off. Turns them on, turns them off, turns them on, turns them off. So that is how it it generates a rising edge for the North Pole being seen, and then the falling edge when the South Pole comes past. Very clever. And these are 30 degrees apart. So that means you've got 30-degree commutation signals. You can have 120-degree commutation signals as well. There you have it. Very good. Just to prove that that is a magnet, it sticks. Let's have a look at the rotor. There you can clearly see 6 poles. Very easy to identify. One, no. 1, 2, 3. Oh, so that's pole pairs. So that's a pair, that's a pair, that's a pair. So that makes that a 2-pole motor. I've got to pay attention to these things. And on the back you can see that's where the windings get overlapped. That's what it looks like inside. There's your slots and laminations and all that good stuff. If we take this, there we can clearly see it attracting the screwdriver in certain positions. And you see what else I'm seeing? Look at how it's holding on to the screwdriver shaft. Okay, the magnets are skewed, right? That's how you reduce cogging in the motor. You either skew the poles so that slot would actually go sideways, like you saw on that motor I stripped a week ago, or you skew the magnets, which is what they've done here, which is why it's holding the screwdriver sideways like that. They skewed the magnets. Something else learnt there, kiddies. Very interesting. So that's that. One side of this is designed to take an encoder in order to produce position and speed feedback for your amplifier, and the other side is where your load that you're driving with the motor is going to be connected to. That's why it's got a shaft sticking out both sides, and you can fit whatever encoder you have depending on what sort of resolution you want to the back of this. It's supplied without one. The amplifier that it works with relies just on the commutation signals from over here to commutate it correctly and tell the magnetic magnetic field which way to rotate in relation to where the magnets are. So if you've got a north and a south present, let's see, it's repelling it. That's 60 degrees away. It's repelling it as well. So there you got north or a south, and then if I turn the magnet around, you can see I know which end is which because of this mark. It's repelling it as well. Interesting. So the amplifier generates a magnetic field which pushes against those magnetic lines, and that's how the motor spins. And your rotating magnetic field stays in phase with your magnets. That's why it's called a synchronous motor. When you give the amplifier a reference, it generates what's called a reference frame, which is the rotating magnetic field in the software simulated. In the software, it generates the rotating magnetic field is what's called a reference frame. And then it wants to get this shaft to move in the same speed and position as the reference frame. Because it knows where the rotor is based on this feedback, it magnetizes the stator to produce that rotation in the rotor. That's how these things work. It is thanks to the modern microprocessors and hardware and IGBTs and good stuff like that that's come about, that we can have brushless motors where everything's inside out. You don't need a commutator. The rotor, the electrical stuff stands still, and you make the permanent magnet spin, and that's called commutation. And this would work with if you had a two-phase motor as well, but pretty much everything works on three-phase motors these days because of lots of physics laws and that sort of stuff. It's practical. we use 3-phase. So that's what that is all about. And I think that wraps up this talk on Wall effect feedback devices inside brushless DC motors. All your brushless power tools these days use them. You find this stuff inside. Pretty much a mature technology these days, and it works well. And these things operate very efficiently and produce good torque at low speeds. They produce high speeds. They're efficient and they're low maintenance because you don't have brushes, which means that you can have this motor hermetically sealed because you don't need cooling, all sorts of stuff. And they're compact. We like them. And you can fit them into all sorts of places. Anyhow, getting out of hand with this ramble. Hope you enjoyed it. Thank you for being here to the end. Ladies and gentlemen, have yourselves a wonderful day further, and I'll be seeing you for more. Take care. Cheers.